Hello everyone. In this video we will discuss NP complete and NP hard problems. Let us understood what is the basic concept of NP complete and NP hard problems. Then in this chapter we are concerned with the distinction between problems that can be solved by polynomial time algorithm and problems for which no polynomial time algorithm is known. For many of the problems we know and study the best algorithms for their solutions have computing times that cluster into two groups. The first group consists of problems whose solution times are bounded by some polynomial or small degrees. Some examples are a searching algorithms or sorting algorithms, and their time complexities for searching is big O of log n and the time complexity of sorting is big O of n log n. That is, we can easily identify the time complexity for such algorithms. Second group made up of the problems whose best known algorithms are non-polynomials. Examples are traveling salesman algorithm or the knapsack problem. And the time complexity for the traveling salesman problem or a knapsack problem is a non-polynomial. That is, the time complexity for traveling salesman problem is big O of n square into 2 raised to n. Similarly, the time complexity for knapsack problem is big O of 2 raised to n by 2. That is non-polynomial time complexity. That is, the theory of NP completeness which we present here does not provide a method of obtaining polynomial time algorithms for problems in the second group, nor does it say that algorithms of this complexity do not exist. Instead, what we do is show that many of the problems for which there are no known polynomial time algorithms are computationally related. In fact, we establish two classes of problems. These are given names NP hard and NP complete. A problem that is NP complete has the property that it can be solved in polynomial time if and only if all other NP complete problems can also be solved in polynomial time. If an NP hard problem can be solved in polynomial time, then all NP complete problems can be solved in polynomial time. All NP complete problems are NP hard, but some NP hard problems are not known to be NP complete. To understand NP complete and NP hard problems, first you have to understand the non-deterministic algorithms and deterministic algorithms. So let us see what do we mean by non-deterministic algorithm and what do we mean by deterministic algorithm. Then every deterministic algorithm has the property that the result of every operation is uniquely defined. Deterministic algorithms agrees with the way programs are executed on a computer. The non-deterministic algorithm remove restriction on the outcome of every operation. Also, non-deterministic algorithm allow to contain operations whose outcomes are not uniquely defined but are limited to specified sets of possibilities. That's why the non-deterministic function introduces three new functions, as one as the choice, second one as the failure, and third one as the success. Then choice is a function arbitrarily chooses one of the element of the set of the inputs S. Then failure signals an unsuccessful completion of the function, and success signals a successful completion of that function, non-deterministic function or non-deterministic algorithm. Then every non-deterministic function includes the three functions as the choice function, failure function, and the success. Choice is any randomly chosen input from the set of inputs. Failure represents unsuccessful completion and success represents successful completion. Here are two sample examples of non-deterministic algorithms to find out the searching and to perform the sorting. Then here the first example will represent the non-deterministic search algorithm, and the second example represent non-deterministic sorting example. Then first discuss what is the non-deterministic search example. Then you have given the array from 1 to n, and you have to choose or you have to choose one element randomly from the given array from 1 to n and initialize it as the j or the index value j. Then if the array a of j is equal to x, the index value you have chosen as a j, then a of j is equal to x, then you have to write j and write the search is successful. Otherwise write 0 and you say the search is failure or search is unsuccessful. That is, you have provided one array with the range from 1 to n, and n are number of elements in the array. Then you have to choose any one index value, the random index value between 1 to n as a j, and you have to compare the value or the array element located at the index value j with the key with the search element x or the key element as a x, and if there is a match, then you can say the search is successful. Otherwise write 0 and say search is unsuccessful. Similarly, discuss another example of non-deterministic sorting. Then algorithm has non-deterministic sorting, and inputs are the array A and with the n as number of elements into array, and this is considered sort all n positive integers. Then for each element from the array for I is equal to 1 to n, you have to do p of I is equal to 0. You have to consider one more similar array variable as b or the equivalent variable as a b, and you have to initialize all the array elements of the array b as 0. Initialize all the b array elements as 0. Then next for I is equal to 1 to n. Then next for I is equal to 1 to n do, then you have to choose one index value randomly in between 1 to n and initialize choice, or you have to choose index value randomly between 1 to n and initialize it to j. Then if the b of j is not equal to 0, then you can say it is a failure. Otherwise b of j is equal to a of I. That is the thing. But if the b of j is 0, then you have to say it is a failure. Otherwise you have to copy the corresponding elements from the position I, and you have to assign it to the index value j to the array variable b. Then finally you have to verify all the elements are all the elements in a resultant array b is in a sorted array or not, by using this for I is equal to 1 to n minus 1 to verify all the order. If b of I is greater than b of I plus 1, then you have to again write it as the sorting is failure or the unsuccessful. Otherwise you can write all the sorted array elements or display all the sorted elements of the array b as from 1 to n, and finally say that sorting is successful. Next, in this presentation, in this slide, we can discuss what is the commonly believed relationship between P and NP examples, or NP hard and NP complete examples. So let us say the P is the set of all decision problems solvable by deterministic algorithms in polynomial time, and NP is the set of all decision problems solvable by non-deterministic algorithms in polynomial time. Then here we can say that all the P is the subset of NP, or we can commonly say that the P is a set of all decision problems solvable by using deterministic algorithm. It belongs to a category as a NP, where NP is the set of all decision problems solvable by non-deterministic algorithms in a polynomial time. Similarly, from second figure, you will get the relationship between P, NP complete and NP hard. That is, from below figure, it's clear that NP hard problems that are not NP complete. Only a decision problem can be NP complete. However, an optimization problem may be NP hard. Optimization problems cannot be NP complete, whereas decision problems can. And there also exist NP hard decision problems that are not NP complete. then we can say that the decision problems, the solvable decision problems are a subset of NP, and again the NP hard is the subset and NP complete is the subset of NP hard.